Hello class. In our last toolbox, we learned to use the limit definition of a derivative to actually start computing derivatives for different functions, and also to derive some rules related to derivatives of two functions that are added to each other. I'm sure this will come as a shock to you, but in this toolbox we're going to continue studying derivatives. We'll also talk about the tides and radioactive decay. So let's get to it. In our last toolbox, we were able to derive an equation for computing the derivative of a function that is the sum of two different functions if we already know or can compute the derivatives of those other two functions. If f of x equals g of x plus h of x, then the derivative of f of x is simply equal to the derivative of g of x plus the derivative of h of x. The second definition up there actually follows directly from the first. If f of x is equal to g of x plus some constant, then we can simply think of it as taking the derivative of g of x plus the derivative of a constant. And since a constant is never changing, the derivative of that constant is 0. So the derivative of f of x is simply equal to the derivative of g of x. Alright, we've got those derivative rules for addition. But next we want similar rules for multiplication. Specifically, we want to ask the questions, if f of x equals g of x times a constant, then what is the derivative of f of x? And if f of x equals g of x times h of x, then what is the derivative of f of x? Let's start off by tackling the first question. If we want to answer this question, it's useful to go back to that limit definition of the derivative. The derivative of f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Alright, let's write out this definition of the derivative while plugging in c times g of x for f of x. This gives us the limit as h approaches 0 of c times g of x plus h minus c times g of x, all divided by h. We can then factor the multiply by c out of this equation, and then if you look at the right-hand side of this equation, you'll see that it basically just looks like the definition for the derivative of g with respect to x. So we can rewrite that the derivative of f of x equals c times the derivative of g of x. Alright, that's the nice general equation that we'd like. If we have a function that is simply a constant times some other function, then the derivative is simply that constant multiplied by the derivative of the other function. Good. Now let's move on and talk about a function that is a product of two other functions. Okay, let's work on figuring out what the derivative will be for a function that is a product of two functions. Or in other words, what do we get for the derivative when we multiply two functions times each other? Well, let's start off similarly by substituting in g of x times k of x for f of x in our limit definition of the derivative. We now see that the derivative of f of x will be equal to the limit as h approaches 0 of g of x plus h times k of x plus h minus g of x times k of x, all divided by h. Okay, next I'm going to do something sneaky. In the middle of this equation, I'm going to subtract g of x plus h times k of x and add that same quantity. Since I'm adding and subtracting the same thing, I'm not actually changing the equation at all. However, I can now start to rearrange the equation in some interesting ways. First, I'm going to pull g of x plus h out of the left side of the equation and k of x out of the right-hand side of the equation, which gives me the limit as h approaches 0 of g of x plus h times k of x plus h minus h of x plus k of x times g of x plus h minus g of x, all divided by h. Alright, let's erase some stuff to clear more space to work. Next, we'll split this in half, which is allowed because the limit of the sum of two functions is the same thing as the sum of the limit of those two functions. Okay, now we've got the limit as h approaches 0 of g of x plus h times k of x plus h minus k of x, all divided by h, plus the limit as h approaches 0 of k of x times g of x plus h minus g of x, all divided by h. Next, we'll note that in the limit as h approaches 0, g of x plus h approaches g of x, and we can factor that term out of the limit and also factor k of x out of the limit. This leaves us with g of x times the limit as h approaches 0 of k of x plus h minus k of x, all divided by h, plus k of x times the limit as h approaches 0 of g of x plus h minus g of x, all divided by h. But of course, if you look at those limits for a moment, you should see that they are equal to the derivative of k of x and the derivative of g of x. So we can see that the derivative of f of x equals g of x times the derivative of k of x, plus k of x times the derivative of g of x. All right, we've derived a very important equation. We figured out that if we want the derivative of the product of two different functions, then we need to calculate the first function times the derivative of the second function, plus the second function times the derivative of the first function. Let's put that to use now. In Toolbox 3.1, we discussed using the product of two sine functions to calculate the tides. The reason that we need two sine functions is that one of those sine functions, with a period of approximately 12 hours, accounts for the impact of the moon on Earth's tides and is related to the speed of the Earth's rotation. And the other sine function, with a period of approximately 2 weeks, takes into account the interactions between the sun's gravitational impact and the moon's gravitational impact. It thus depends on the moon's orbit around the sun. The moon's orbit around the Earth. The moon's orbit around the Earth thus affects the amplitude of the tides, and hence this function, g of t, basically goes into the part of the equation where you would normally put a constant value for the amplitude. When we graph h of t, which basically tells us the height of the tides, we see that the tide goes up and down twice per day. But the amplitude of the tide varies based on whether we're in a spring tide phase or a neap tide phase. Now, there are a lot of reasons why we might care about the tides, but one of them is if we're studying intertidal communities like the one in the picture up at the right. Intertidal communities have strong environmental forcing driven by the tides. At high tide they are submerged, and at low tide they are exposed to the air. Thus the ecological pressures facing these organisms are strongly coupled with the rate at which the water is rising or falling. And of course, since our function is telling us the height of the tides, taking the derivative of the function h of t will tell us how rapidly the tides are rising or falling. So let's go ahead and calculate that. All right, let's start by remembering those really important rules that we just derived. First, we can see that h of t is equal to a constant times the other two functions. So we'll use our rule for multiplying by a constant, which tells us that if f of x equals c times g of x, then the derivative of f of x equals c times the derivative of g of x. This allows us to write that the derivative of h of t will be equal to 2 times the derivative of f of t times g of t. Second, we've got the rule we just derived telling us that if we want to find the derivative of the product of two functions, then we need to compute the first function times the product of the second function plus the second function times the derivative of the first function. So we can write that the derivative of f of t times g of t equals f of t times the derivative of g of t plus g of t times the derivative of f of t. We can then combine those two equations and see that the derivative of h of t should be equal to 2 times the sum of f of t times the derivative of g of t plus 2 times g of t times the derivative of f of t. All right, that means that if we want to compute the derivative of h of t, all we really need to do is figure out the derivative of f of t and g of t. Okay, we haven't talked about taking the derivative of a sine function yet, so it's probably time to do that. But first, let's clean things up a bit. Okay, let's talk about the sine and cosine functions. The top plot shows the sine function, which should, of course, be very familiar to you by now. And the bottom function shows the derivative of the sine function, which can which we can estimate using our geometric definition of the derivative. Initially, sine of x is increasing, so the slope is positive and the derivative is positive. The slope decreases until sine reaches its peak, and then the slope becomes negative and the derivative becomes negative. Once sine reaches its minimum at x equals 3 pi over 2, it will start to increase again, and the slope will be positive until everything repeats itself. Because of course, the sine function is cyclic. Alright, if we watch that derivative function being drawn, it should make sense as the derivative, but it should also look familiar to you. It should just look like the cosine function. The derivative of sine of x is actually equal to the cosine of x. This is an important result that you should remember, because it lets you compute the derivative of a sine function. And if you ever forget, for instance, whether the cosine function is the derivative of the sine function or the sine function is the derivative of the cosine function, you should be able to just graph them, look at those graphs, and figure out which makes more sense. Clearly, the cosine makes sense as the derivative of the sine function, because when the sine function is decreasing, the cosine function is negative, and when the sine function is increasing, the cosine function is positive. Okay, that's an important result, but it doesn't actually directly answer any of the functions above that we need derivatives of. We need to think about how changing the amplitude or the period of the sine function will affect its derivative. Let's start with changing the amplitude. This time I graphed the derivative of 2 times the sine of x, and we're also computing, I graphed the function of 2 times the sine of x, and we're also computing its derivative. If you think about it, if we increase the amplitude by a factor of 2, what that really means is that the derivative will always have to change twice as fast, either in the positive or the negative direction. So we're really also stretching the derivative by a factor of 2. This also makes sense if we think about one of the rules that we computed earlier in this toolbox. Remember, we determined that if f of x equals c times some function g of x, then the derivative of f of x is simply equal to that constant c times the derivative of g of x. In this case, g of x is sine of x and c is 2, so this tells us that the derivative of 2 times sine of x is equal to 2 times cosine of x. And more generally, we can write that for any constant c, the derivative of c times the sine of x will be equal to c times the cosine of x. Alright, we're getting a bit more general now, but what happens if we want to change the period? This time, I've changed the period, and we're looking at the sine of 2x. Remember that the sine of 2x will have a period that is only half the length of the sine of x. Its period is pi instead of 2 pi. That means it repeats itself twice as often. So let's think about what that is doing to the derivative. If the function is still going from -1 to 1, because it still has the same amplitude as sine of x, but it is doing it twice as often, or in other words, it is moving twice as fast, then that means that the derivative must be twice as large, because the derivative is the rate of change. So intuitively, it makes some sense that if we decrease the period by 1/2, then we will double the amplitude of the derivative. If we decrease the period of the function by 1/2, we will also, of course, decrease the period of the derivative by 1/2, since the periods of the function and its derivative have to be the same. If the function repeats itself every pi, then the derivative must repeat itself every pi as well. Okay, so our intuition tells us that the derivative of the sine of 2x should have an amplitude of 2 and a period of pi. We can thus write that as the derivative of the sine of 2x equals 2 times the cosine of 2x. I'm not going to prove it here, although you'll learn how to prove it in the next toolbox. But the derivative of the sine of any constant times x equals that constant times the cosine of that constant times x. A more general equation can be written stating that the derivative of c times the sine of b times x equals c times b times the cosine of b times x. Note that in this equation, c and b are both scalar constants. All right, next let's actually use this important equation to find the derivative of h of t by first finding the derivatives of f of t and g of t. All right, let's start by computing the derivative of f of t. We'll use the equation for the derivative of a sine function that we just calculated, noting that with f of t, we need to substitute 0.5 in for c and 2 pi times 24 over 12.5 for b. These values, of course, are coming from our equation for f of t. When we plug them into our equation to calculate the derivative of f, we find that the derivative of f equals 0.5 times 2 pi times 24 over 12.5 times the cosine of 2 pi times 24 over 12.5 times t. Next, we'll do the same thing for g of t. This time c equals 0.25 and b equals 2 pi over 14. So the derivative of g equals 0.25 times 2 pi over 14 times the cosine of 2 pi over 14 t. Next, we need to use our equation for the derivative of the product of two functions. We already calculated that the derivative of h of t is equal to 2 times f of t times the derivative of g of t plus 2 times g of t times the derivative of f of t. So if we plug in those values, we find that the derivative of h of t equals 2 times 0.5 times sine of 2 pi times 24 over 12.5 t times 0.25 times 2 pi over 14 times cosine of 2 pi over 14 t plus 2 times 0.5 plus 0.25 times sine of 2 pi over 14 t times 0.5 times 2 pi over 2 pi times 24 over 12.5 times cosine of 2 pi times 24 over 12.5 t. If we graph this equation, we can start to see how the derivative will vary in time. The derivative has that familiar sinusoidal pattern that we've come to expect from our trigonometric functions, although obviously the amplitude of the waves in the derivative is greater than the amplitude of the waves in h of t. This higher amplitude is because the period of the function is shorter. So although the function is still only going up or down by less than 1 as the tide comes in and out, this happens faster than what we would get if the period was 2 pi. Remember, 2 pi is equal to approximately 6.28, so that would mean this repeats only about once per week, when of course the tides actually repeat twice per week. Since everything is happening more rapidly, the derivative is greater. We also see that, unlike our normal sine curves, for which the amplitude of the derivative stays constant, here we've got a varying amplitude in the derivative, which of course makes sense, because the amplitude of h of t varies between when we are having spring tides or neap tides. This function now allows us to calculate how rapidly, in units of meters per day, the tide will be going in or out at any particular day. This can be really useful information if we want to plan experiments to test the stress that intertidal organisms face as a result of changing environmental conditions. All right, next let's talk about radioactive decay and some of the important calculations you'd need to make if the EPA tasked you with determining the danger associated with radioactive waste left over from a nuclear power plant. Well, we know that radioactive isotopes decay away at a fixed rate such that half of them disappear over a period of time equal to the half-life of the isotope. Well, we learned in Toolbox 2.2 that we can write out a function for radioactive decay using an exponential function with a negative exponent. When the exponential function is written with a negative exponent, we often refer to it as exponential decay. In this equation, n of t is the number of atoms of the radioactive isotope as a function of time. N naught is the initial initial amount of the radioactive material. T is time, and lambda is the decay constant for the radioactive isotope. The decay constant varies a ton for different isotopes. Some isotopes, like beryllium-14, have large decay constants in the range of 1,000 per day, and thus have half-lives of only seconds. Others, like phosphorus-32, have a decay constant in the range of 0.5 per day that gives them a half-life in the range of weeks. Uranium-232 and plutonium-238 have decay constants of roughly 2 times 10 to the negative 5, which gives them half-lives on the order of 100 years. Carbon-14, which you've probably heard of, has a much lower decay constant of 3 times 10 to the negative 7, which gives it a half-life of about 5,730 years. And uranium-238 has a decay constant of 4 by 10 to the negative 13, which equates to a half-life that is almost the age of the Earth. Alright, so if we want to know how much uranium-232 might be left after 1 year, and we can plug in 365 for T and plug in the appropriate decay constant of 2.8 by 10 to the negative 5 for uranium-232. We can then use our radioactive decay function to calculate that after 1 year, N of 365 equals N0 times e to the 2.8 by 10 to the negative 5 times 365, which is equal to 0.99 times N naught. So 99% of the uranium-232 will still remain 1 year later. We can also, of course, graph this function to see how the amount of uranium-232 will change even further into the future. This graph shows us the fraction of the radioactive material that remains as a function of time in days. Note that this is actually in days times 10,000 because it takes so long for the uranium-232 to decay away, since, of course, none of us are used to thinking in terms of days times 10 to the times 10,000. Let's replot it by converting from days to years on the x-axis. Now we can clearly see that after 100 years, a little less than 40% of the uranium-232 remains. Okay, that's useful. That's an important thing to be able to calculate. But let's remember that it's not actually the amount of material there that matters to us. What really matters is the amount of radioactive decay. We care about how many alpha, beta, or gamma particles are being emitted as a function of time, because it is those alpha, beta, or gamma particles that are harmful to us. And of course, the reason that I'm bringing this up is that the derivative will allow us to compute how many of these particles are being emitted. Remember, the reason that the uranium-232 is disappearing is that it is decaying away, so that means that the radioactivity levels are directly tied to the decay rate. In other words, the derivative of the abundance of the material actually tells us the radioactivity of that material. Okay, so let's figure out how to calculate the derivative of an exponential function like that. But let's start off simply. We'll start off by figuring out what the derivative of f of x equals e to the x is. Remember that e is just a constant number, like pi. E is actually equal to 2.718281828, etc., etc. It's just a number, but like pi, it's a special number. So let's go ahead and work on the derivative of e to the x. Remember that e to the x really means multiplying e times itself x times. So f of 2 equals e to the 2, which is 2.71828 times 2.71828. Alright, as we look into what the derivative of this function will be, let's remember our limit definition of the derivative, which tells us that the derivative of a function is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. Let's just try approximating the derivative of f of x at x equals 2 by making h smaller and smaller. First, we'll try h equals 1. When we try h equals 1, we are really calculating f of 2 plus 1 minus f of 2 divided by 1, which is equal to e cubed minus e squared divided by 1, which is equal to 12.695. Okay, but let's try to get a bit more accurate. So let's try h equals 0.1. Now we're calculating f of 2 plus 0.1 minus f of 2 divided by 0.1, which equals e to the 2.1 minus e squared divided by 0.1, or 7.7711. And of course, we can get a bit more accurate by trying h equals 0.01, which turns out to be equal to 7.4621, or h equals 0.001, which gives us 7.3928. If you're paying attention, you'll notice that as we're making h smaller, our estimate of the derivative is getting more accurate, and it's actually getting a little bit lower each time, but it's decreasing by less each time. We can actually graph e to the 2 plus h minus e squared divided by h as a function of h, and you'll see that eventually, as it approaches h equals 0 on the left-hand side of this graph, it actually approaches a value of slightly less than 7.4. And actually, if you look at what f of 2 equals, it's also slightly less than 7.4. So it seems like the derivative of f of x evaluated at x equals 2 is approaching a number that's pretty close to the value of f of 2. All right, let's try this again, picking another value for x. Let's try x equals 3 this time. All right, now we compute that f of 3 equals e cubed, which is equal to 20.0855. Okay, let's try to estimate the derivative of f of x when x equals 3. Let's try using our derivative definition, our limit definition of the derivative again, with h equals 1. This time we've got f of 3 plus 1 minus f of 3 all divided by 1, which is equal to e to the 4th minus e cubed divided by 1, and 34.5126. If we make h smaller and try h equals 0.1, we've got f of 3 plus 0.1 minus f of 3 divided by 0.1, which is equal to e to the 3.1 minus e cubed divided by 0.1, and 21.1241. If we try an even smaller h of 0.01, we calculate a value of 20.1863. And if we go even smaller to h equals 0.001, we get a value of 20.0956, which again tells us that the derivative of f of x evaluated at x equals 3 is clearly really close to the value of f of 3. And this is actually the point of the special value e. The special value e is a special value because the derivative of f of x equals e to the x actually is e to the x. The derivative is just the original function again. In the same way that we have the special number pi because it is the ratio of the circumference of a circle to its diameter, we have the special number e because if you raise e to the x power, the derivative of that function is the function itself. It has the special property that if you travel along that function, you're always increasing by an amount equal to what your value is at that point. Okay, let's take a look at what that means graphically. All right, if we watch this graph, you'll see the original function f of x along with the slope of its tangent line plotted on top, and on the bottom you see the derivative of the function, computed using our geometric definition of the derivative. So as we watch this graph go through, we see that yes, in fact, the slope is changing in a gradual way such that at any point the derivative of f of x is equal to f of x. All right, that's great. We've convinced ourselves that if f of x equals e to the x, then the derivative of f of x also equals e to the x. This is one of the really important derivative equations that you should remember. The derivative of e to the x is e to the x. But of course, that's not all we need to know. Remember that for radioactive decay, we're not using a function that is equal to e to the x. We're using a function that is e raised to the product of negative the decay rate times x. So we need to know what to do if there's a constant in there multiplied by the x. So let's just plug in 2 and give it a try. All right, if we run the same thing with f of x equals e to the 2x, you can see that everything increases much faster. Note that the y-axis here goes up 2 times 10 to the 4, or in other words, it goes up to 20,000. In the last graph, the y-axis only went up to 150. Okay, we can see that since f of x increases much faster, the derivative clearly goes up faster as well. Note, as you watch this, that the derivative actually increases faster than the function f of x. The lower graph is really a bit higher than the upper graph. So remember that the derivative of e to the x is e to the x. However, clearly, the derivative of e to the 2x is not e to the 2x. Instead, it's something a bit higher. In fact, the derivative of e to the 2x is actually 2 times e to the 2x. And more generally, we can write that the derivative of e to the ax is a times e to the ax. That's another really important general rule for derivatives. The derivative of e raised to some constant times x is equal to the constant times e raised to the power of that constant times x. Another way that we could say that same thing is to say that if f of x is equal to e to the ax, then the derivative of f of x is equal to a times f of x. All right, so now we can apply this to our radioactive decay equation. All right, let's move this equation out of the way and remember the equations we had for the amount of radioactive material we'll have left as a function of time. We can now find the derivative of this equation. In this equation, lambda is the equivalent of a in our general equation. So we can calculate that the derivative of n of t is equal to n naught times negative lambda times e to the negative lambda t, which means that the radioactive decay, measured in units of per day, will be equal to the original number of radioactive atoms that we had, times lambda, which is the decay rate, times e to the negative lambda times t. Of course, we don't often talk about decays per day, but we often do talk in terms of becquerels, which means the number of decays per second. So to find that, we just need to divide by the number of seconds in a day. Okay, so this simple derivative has allowed us to compute very accurately how much radioactivity there will be in the future if all we know is the decay rate of the isotope, which we can look up online, and how much of that isotope we start off with. Okay, let's review some of the key things that we've learned in this toolbox. First, we learned that if our function is equal to a constant times some other function, then the derivative of our function is simply equal to the constant times the derivative of the other function. Next, we learned that if our function is equal to one function times another function, then the derivative of our function is equal to the first function times the derivative of the second function, plus the second function times the derivative of the first function. Then, we learned that if our function is equal to a constant times the sine of some other constant times x, then the derivative is equal to the first constant times the second constant times the cosine of the second constant times x. And finally, we learned that the derivative of e raised to a power of some constant times x is equal to that constant times e raised to a power of that constant times x. All right, that's it for this toolbox. In our next toolbox, we will dive into the chain rule for derivatives. Don't forget to take the quiz on Canvas.